morning everyone. So, welcome to this class of modeling in membrane separation process. So, what we did in the last class, we were looking into the modeling of cross flow filtration, and this modeling is applicable for reverse osmosis, ultrafiltration, nanofiltration, even for microfiltration. Now, in this class, in the last class, whatever we did, we formulated the governing equations and the of the solute mass balance within the mass transfer boundary layer, and next then we have found out that this is a problem of fully developed velocity profile and developing mass transfer boundary layer. So, we have written down the solute mass balance in a two-dimensional form within the mass transfer boundary layer. Now, in today's class, we will be formulating the boundary conditions associated with this problem, and then we will be looking into the solution, and then we will see how this solution can be utilized for the prediction of the system performance in order to calculate the permeate flux and permeate concentration. Therefore, if you remember, the governing equation was 3 u0 y by h del c del x minus vw del c del y is equal to d del square c del y square. Now, we will be writing down the respective boundary conditions. At x is equal to 0, there is a so called initial condition to this problem, c is equal to bulk concentration. At y is equal to delta, c is equal to c naught, again the bulk concentration, or delta is the edge of the boundary layer, mass transfer boundary layer. But as we have argued in the last class, that we are dealing with a system where the solute will be having very low diffusivity and hence very high mass transfer, very high Schmidt number, and thickness of boundary layer is mass transfer boundary layer is inversely proportional to the Schmidt number. So, therefore, we are talking about a boundary layer thickness, mass transfer boundary layer thickness, which will be around 1% of the total channel dimension. In that case, that we can see that beyond the mass transfer boundary layer, majority of the channel, the concentration remains bulk concentration. So, we can safely replace this boundary condition as at y is equal to infinity, c is equal to c naught. Now, let us set up the boundary condition at, so we need one more boundary condition on y, because this equation is ordered 2 with respect to y. So, at y is equal to 0, we will be having the at the steady state, all the fluxes at the towards the membrane will be, all the solute fluxes towards the membrane will be equal to 0. So, that will be giving you the Vw c minus Cp plus d del c del y will be equal to 0. So, the first term will be the convective solute flux towards the membrane surface, second term is the convective solute flux away from the membrane surface, and the third one is the diffusive solute flux away from the membrane surface. So, now these three conditions will be setting up the complete definition of the problem, and as you have already known that we have already solved the one dimensional problem related to the mass transfer boundary layer, and we have already solved this. Now, if you can remember that the boundary condition of the two dimensional problem has now was the governing equation for the one dimensional problem. So, now let us try to solve this set of equation. If you look into the governing equation is a parabolic partial differential equation, and one of the boundary condition is residing at infinity. So, there are two thumb rules for having a similarity solution. To a partial differential equation. These are, if the PD must be a parabolic one, and second, one of boundary condition resides at infinity. If these two thumb rules are met, then this governing equation may admit a similarity solution. So, what is why the similarity solution is so important in case of boundary layer problems, that has to be very clear to everyone. So, similarity solution is, suppose we are talking about any boundary layer problem. Let us say we are talking about a mass transfer boundary layer in this case. So, the boundary layer grows over the wall or over the membrane surface. Now, if you look into the concentration profile, the concentration profile is assuming the value is assuming C is equal to C naught at the edge of the concentration boundary layer or mass transfer boundary layer, and the concentration is C at the membrane surface, and this Cm concentration of solute at the membrane surface will be a function of x. So, at every point you will be having a profile something like this, and if you look into the profiles are similar in nature, and these profiles are called self similar profiles. So, whenever we will be having the self similar profiles, we will be having the self similar profiles in the case of all sorts of boundary layer problems, whether it is a thermal boundary layer, whether it is a mass transfer boundary layer, whether it is a hydrodynamic boundary layer, we will be having the self similar profiles for velocity field in case of hydrodynamic boundary layer, temperature field in case of thermal boundary layer, and concentration field in case of mass transfer boundary layer. So, this self similar profiles will be this therefore, they will be function of y and x. The delta will be the boundary layer thickness delta will be essentially a function of x. Now, if you plot concentration profile as a function of x or as a function of y, at y is equal to 0, this value is Cm. Okay, it will be very high value, and y is equal to infinity or delta, this is C naught. So, you will be having a value of a profile something like this at a particular x location. This will be at a particular x location, because Cm will be varying, and then this will be at a particular x location. Okay. So, now when we will be defining a parameter eta which will be nothing but y by delta, then all these curves will be coincide and they will be superposing on a single curve. So, therefore, we will be reducing the number of independent. So, delta will be a function of x, we will be reducing the independent variable x and y into one single variable, that is the similarity variable, and this is also known as the combined variable. This combined variable is eta. So, whenever we will be plotting the concentration profile or temperature profile as a function of eta, so all the curves will collapse on a single curve, and we will be having a variation with respect to one variable only, that is known as the combined variable or similarity parameter. And therefore, what is the final advantage of this? The advantage of this will be reducing the two independent variable system into one independent variable system. In other words, we will be converting a partial differential equation into an ordinary differential equation. So, eta is known as the similarity parameter, and similarity solution, and the solution method is known as the similarity solution, and the similarity solution will be obtained if we have a partial differential equation which is parabolic in nature, and one of the boundary condition is residing at infinity. Okay. So, in this case also we will be our problem satisfies that thumb rule, and we will be admitting a similarity solution in this case. Okay. So, therefore, let us look into the how to evaluate the similarity parameter. Now, similarity parameter can be obtained if let us do an order of magnitude analysis. Analysis of governing equation at the edge of the boundary layer. So, let us look into the governing equation once again. 3 u 0 y by h del c del x minus v w del c del y is equal to d del square c del y square. So, we evaluate at the edge of the boundary layer, and any boundary layer will be satisfying two typical conditions at the edge of the boundary layer, whether it is a velocity boundary layer, thermal boundary layer or mass transfer boundary layer. What are these? These conditions, two conditions are known as the boundary layer conditions. These are basically at the edge of the boundary layer, the dependent variable will be assuming the value of that of the free stream. For example, at y is equal to delta, c is equal to c naught if it is a mass transfer boundary layer. At y is equal to delta, t is equal to t infinity if we are talking about a thermal boundary layer, and at the edge of the boundary layer u is equal to u infinity if we talk about the hydrodynamic boundary layer. Similarly, another condition will be satisfied at the edge of the boundary layer, that is the gradient of the dependent parameter with respect to y will vanish. That means, at y is equal to delta, del c del y will be equal to 0, at y equal to delta, del t del y will be equal to 0 and del u del y equal to 0 in case of hydrodynamic boundary layer. So, therefore, will be at the edge of the boundary layer del c del y will be equal to 0. So, this term will be gone, and let us have a we evaluate the rest of the equation at the from the very beginning, from at x equal to 0 to a small value of x. So, 3 u 0 at the edge of the boundary layer y is equal to delta. So, this will be delta by h. So, del c will be delta c, that is occurring between the in the boundary layer, and delta x will be x minus 0 if we start from x equal to 0, and d del square c will be again a sort of delta. So, if you really do a numerical calculations using the finite difference method, that you can see that del square c is nothing but a kind of difference delta c. So, this will be order of magnitude of delta c, and delta del y square will be y delta minus 0 square of that. So, that will be giving you an estimate of how delta varies with x. So, this will be delta cube is equal to dx. So, delta cube will be nothing but h dx divided by 3 u naught, and delta will be h d by 3 u naught times x raised to the power 1 upon 3. So, therefore, this will be the variation of delta, the mass transfer boundary layer, in this case with respect to s. In fact, delta is varying as x to the power 1 upon 3. So, therefore, we will be able to now derive the similarity parameter, and the similarity parameter is, we defined eta is equal to y by delta. So, y and delta will be writing as u 0 over h d raised to the power 1 upon 3 1 over x to the power 1 upon 3. So, this will be nothing but u 0 h d raised to the power 1 upon 3 y divided by x to the power 1 upon 3. So, we if you why we have put this term will be there, because if you include, so u naught is a constant, h is the geometry half height of the channel, d is the solute diffusivity which will be acting as which will be assumed to be constant. So, the combination of all these parameter, you can see that eta will be a dimensionless number. So, eta does not have a dimension, the similarity parameter, and now what we will be doing next, we will be expressing all the derivatives of the governing equation del c del x, del c del y, del square c del y square in terms of the similarity parameter eta. So, in terms of the combined variable parameter eta. So, therefore, we can reduce the so there will be no independent variable x and y in the governing equation, there will be only one parameter eta into the governing equation. So, partial differential equation will be boiled down into an ordinary differential equation. So, now next what we will be doing, will be deriving, will be expressing all the partial derivatives in terms of eta or the similarity parameter. So, let us do that. So, del c del x will be nothing but dc d eta, because since now c will be a sole function of eta, the partial derivative will become a complete derivative or total derivative. dc d eta minus 1 upon 3 u 0 h d raised to the power 1 upon 3 y x to the power 1 upon 3 times x, and this will be nothing but minus eta divided by 3 x dc d eta. And similarly, you can derive del c del y as u0 h d raised to the power 1 upon 3 1 or x to the power 1 upon 3 d c d eta, and second derivative del square c del y square will be nothing but one more derivative of del c del y. So, if you really do that, the expression becomes u0 by h d raised to the power 2 by 3 1 over x to the power 2 by 3 d square c d eta square. Now, if we substitute this the partial derivative in the governing equation, and we will do and if you remember, the governing equation is 3 u0 y by h del c del x minus v w del c del y is equal to d del square c del y square. So, I am replacing del c del x from here into this equation, del c del y here, and del square c del y square into this, and then after doing a simplification, the final version of the equation becomes eta square minus v w h x divided by u0 d square raised to the power 1 upon 3 d c d eta is equal to d square c d eta square. So, we will next what we will be seeing that the partial differential equation has now boiled down into an ordinary differential equation. So, now let us tackle with this part of the equation. So, as we have discussed earlier that as the boundary layer grows in thickness, it offers more resistance against the solvent flux. So, therefore, the thickness of the boundary layer, initial part of the boundary layer, that means initial x location of the channel, the resistance against the solvent flux will be very less, and one will be getting a very high solvent flux. As the boundary layer thickness grows in thickness, then it will be offering more resistance and the solvent flux will be decreasing. So, therefore, permeate flux or the solvent flux or permeate flux is inversely proportional to the thickness of the mass transfer boundary layer. So, V w is inversely proportional to delta, and we have already observed that delta is directly proportional to the x to the power 1 upon 3. So, V w is inversely proportional to the x to the power 1 upon 3. That simply indicates that V w x to the power 1 by 3 is a constant. Okay. So, we define a constant, the term in this term V w x to the power 1 upon 3, including the other terms. So, this is constant, h is constant, u0 is constant, d is constant. So, we define the whole term becomes a constant, and we define that constant as a. So, we define V w h x divided by u0 d square raised to the power 1 upon 3 is a constant a. Okay. So, once we do that, then the governing equation becomes now very simple, d square c d eta square is equal to minus eta square minus a d c d eta. And now, if you see that we have, since we have already observed that eta is a non-dimensional parameter and a is also non-dimensional parameter. So, if you look into the dimension of a, let us look into the dimension of a. What is the dimension of V w? Dimension of V w is meter per second, and h is in meter, x is in meter, u0 is in meter per second, and d square is meter square per second. So, it will be meter to the power 4 second square raised to the power 1 upon 3. So, this becomes meter per second, and this will be second cube by meter cube to the power 1 upon 3. So, this will be meter by second into second by meter. So, it will be dimensionless. So, they will be cancelling out. So, therefore, let us make the numerators the variable c to be non-dimensional. So, we write c star is equal to c by c naught. So, therefore, d square c star d eta square is equal to minus eta square minus a d c star d eta. So, this becomes the governing equation of concentration profile within the mass transfer boundary layer. Now, what we will be doing next will be, in order to solve this equation, we need to have two conditions on eta, because it is of a second order with respect to eta, and we will be formulating those two boundary conditions in terms of similarity parameter eta. And if you remember, we had two conditions on y. So, we will be converting those two boundary conditions into non-dimensional parameter, combined similarity parameter eta, and then we will be solving this equation. So, let us do that. So, at y is equal to 0, if you remember, C was equal to C naught, what y equal to infinity, C is equal to C naught. At y is equal to infinity means eta is equal to infinity, C star is equal to 1. At y is equal to 0, we had V w C m minus C p plus d del C del y was equal to 0. C, it was in fact C minus C p, but C at y is equal to 0 is nothing but concentration of solute at membrane surface. So, in terms of similarity parameter, if you really, so if you do that, it will becomes C m R r. We can remove C p, we can replace C p in terms of R r, definition of real retention, as we have discussed in the last class, d del C del y is equal to 0. So, therefore, in terms of similarity parameter, if you substitute the expression del C del y in terms of the similarity parameter, after simplification, this will turn out to be d C star d eta plus a C m star R r equal to 0 at eta equal to 0, because y equal to 0 means at eta equal to 0. Okay. So, we have formulated the two boundary conditions and we have the governing equation. Now, the governing equation let us solve. So, d square C star d eta square is equal to minus eta square plus a d C star d eta. Let us say d C star d eta is equal to z. So, d square C star d eta square is nothing but dz d eta. So, dz d eta will be is equal to minus eta square plus a z. So, dz by z is equal to minus eta square plus a d eta, and one integration will give you ln z. So, it will be z plus k 1 is equal to k 1 exponential minus eta cube by 3 minus a eta d eta. And what is z? Z is nothing but d C star d eta. Z is nothing but d C star d eta. So, we will be having one more integration in terms of with respect to eta. So, d C star d eta is equal to k 1 exponential minus eta cube by 3 minus a eta d eta. So, one more integration will give you the expression of C star as k 1 exponential minus eta cube by 3 minus a eta d eta plus k 2. So, these will be giving you the complete profile of concentration within the mass transfer boundary layer. And now, we evaluate the integration constant k 1 k 2 from the boundary condition at eta equal to 0. We have at eta equal to 0, we have d C star d eta plus a C m star R r equal to 0. So, what is d C star d eta? D C star d eta is equal to this expression. So, okay, this will there will be no d eta there. So, we evaluate d C star d eta at eta equal to 0. At eta equal to 0, it is exponential 0 1. So, it will be value of k 1. So, this will be k 1 plus a C m star R r equal to 0. So, let's find out what is the value of C m star at what is C m star? C m star is C star evaluated at eta equal to 0. So, therefore, Cm star is equal to at eta equal to 0 means we evaluate this Cm star at eta equal to 0, this limit 0 to eta. So, this will be from 0 to 0. So, this integration will be off. So, Cm star will be nothing but k 2. So, therefore, k 1 plus a Cm star is k 2. So, I will write it clearly k 1 plus k 2 a RR will be equal to 0. So, now let us look into the other equation. Let us look into the other boundary at eta equal to infinity, C star equal to 1. So, therefore, 1 is equal to k 1 0 to infinity exponential minus eta cube by 3 minus a eta d eta plus k 2. So, this will be 1 is equal to, and this will be a definite integral varying from 0 to infinity if we know the value of a. So, if you know the value of a, this integral will be returning us some value. So, let us write down this integral as k 1 I plus k 2. So, I have two governing equation for evaluating k 1 and k 2, and we can get the expression of k 1 and k 2. So, let us get that k 1 from the first one we will be getting q 1 is equal to minus k 2 a r r, and from the second equation you will be getting, I write I replace k 1 as k 2 a r r I plus k 2 is equal to 1. So, k 2 becomes 1 over 1 minus a r r I, and k 1 becomes minus k 2. So, minus a r r divided by 1 minus a r r I. So, what we now require is that Cm star is equal to nothing but k 2, and this k 2 is equal to 1 divided by 1 minus a r r I, where the integral I is from 0 to infinity exponential minus eta cube by 3 minus a eta d eta. So, this will be, so what we have done, so these two relations are extremely important. So, whatever we have done is that we evaluated the mass transfer concentration profile in the mass transfer boundary layer as C star is a function of eta, which will be basically combined variable y in terms of y and x, and eta is basically varying as y divided by x to the power 1 upon 3. So, we evaluated the concentration profile at y equal to 0 or eta equal to 0 in order to get the Cm as a function of k 2 r r etc. I etc. So, now in the next class what we will be seeing that how this expression can be hooked up with the transport laws through the porous membrane, and then we can get the system prediction perfectly. Thank you very much.